numerical Python or NumPy, but then we're kind of starting it again from like a really strong, so that we all have a really strong foundation on what NumPy is. And yeah, but before I get started, I want to explain what NumPy is again. And NumPy, remember, it was like a Python module that we use for data science mainly. And what NumPy actually stands for is numerical Python. So whenever we have to work with lots of data or lots of information and work with numerical computation, we oftentimes use NumPy. And NumPy is a module similar to how we have random modules in different languages like Python, Java, and C++. And we have to import our modules using this statement, import NumPy, but we put as NumPy as NP at the end so that it simplifies the amount of typing that we have to do. Okay? And you might be wondering, why do we use NumPy rather than the regular Python list? Well, we could use regular Python lists to do all sorts of different calculations, but then here's the problem. Unlike other languages like C and C++, it's very not time efficient, so time inefficient. But before I explain a bit more on why we use NumPy, I want to take a look at what data types in Python we have. So remember, we have integers, booleans, so many different data types in Python. But we also have data types with NumPy, and we have data types with different languages. But in Python, we would say x is equal to 10, and we don't necessarily need to declare the type of variable. But in, let's say, C++, we always have to put int x is equal to 10 with the semicolon at the end. So x in this case would be an integer that is explicitly declared, but in Python we actually don't have to explicitly declare it, and that's something that we refer to as dynamic typing. You don't have to memorize what dynamic typing is, but you just have to understand the concept of what dynamic typing is. And that just simply refers to how our data type is automatically assigned. So as I said before, in Python, when we say x is equal to 1, there's a lot of different stuff going on because Python actually has to figure out what data type is 1, which is an integer, right? So a Python integer would actually have like a Py object head and then something that refers to what data it's actually storing. But in C, and we also have a bunch of other information that Python has to store for that singular variable. But in C, what we can do is we can point to a location in our memory and just store 1 in that memory because we explicitly declare that variable. And so if we have like a list in Python that has true, 10 as a string, 1, and then 1.2, we have 4 different data types in here. And each element within the list is its own object. So we have to store all that information in that singular list. But if we have a list of 10 integers, it's not really necessary to store, okay, what is the data type of our first element, our second element, our third element, so on and so forth. So we wouldn't need to store that information. So let's take a look at this diagram first. And what this diagram is trying to illustrate is the difference between a NumPy array and a Python list. So a Python list would just store its length, right? So remember when we did len with the length function, we actually could find the length of the list pretty quickly. And we have our object head and our items. So our items, how it's actually stored is it stores the memories or where it's pointed to. And our memories then point to the actual values in our memory, okay? So if you know a bit about pointers, these are all pointers, and these pointers store to the actual values. And these values are very complex. Remember, with this diagram, we had our Py object head and our digit. But in languages like C, what we can do is we can actually have a contiguous memory or contiguous storage of array. So you can have 1, 2, 8, 4, 8, 16, as you can see from this diagram, and have a single pointer pointing to the head of this array. But in Python, it's a bit more complex than that if we use a regular list. But if we use NumPy, what it actually does is it kind of mimics C++ in a way so that we can store these data in contiguous fashion. And moreover, we also have dimension and strides and different attributes associated with the NumPy array, which we will be talking more about later on. Don't worry about these things. Just know that the difference is that NumPy arrays, they store data continuously, but in Python's regular list, the memories are stored and then it's associated with the actual data. So it kind of gets rid of this middle spot here and makes it a lot more easier for us to work with. And also something else I want to point out is that with NumPy arrays, you can only have one specific data type, so you can't have a mix of data type. So you can't have an integer with a float or a boolean with a string, for example. You can only have one thing in that singular array. So we talked about why it's so useful to use NumPy arrays, and we covered on that last week a little bit, but we didn't go into as much detail as we did today. But now we'll talk about how we can explicitly declare our NumPy arrays, and then how we can work with our NumPy arrays. So to declare NumPy arrays, we must have the same data type as I've said, and that's because we have to store each of them in a contiguous fashion. So we can explicitly declare data type using dtype, also, and this was a corgs argument. Remember, the corgs was the one where we had keyworded arguments from lesson 1, which we had just had a quiz on. So if we do dtype is equal to float32, this would refer to a 32-bit float. And then we would be storing 1, 2, 3, 4. But these aren't floats, these are integers. Well, what Python does is it converts these floats it converts these integers into floats. So 1 would turn into 1.0, which is the same thing. But if we don't put this dtype argument in, remember corgs were optional arguments, right? We don't necessarily need to have these arguments. It would just automatically assign a data type to the array. So these functions that I'm going to talk about next. You have to memorize them. Like, it's good that you have them memorized, so our next quiz won't be open book, unfortunately. But it's not too many functions to memorize, but they are used quite often in data science, and I do want you to get familiar with them. Anyways, but they're pretty simple, don't worry. So to define NumPy arrays, it's very similar to, it's not quite similar to Python's list, but we just have different functions to do them. If we do np.zeros, what this will do is fill up an array with 0, but the Python equivalent would be doing 0 times 10. And I just explicitly declare these data types, dtype int and dtype float. Okay. We could also have an array full of ones as well, just with the ones function and the zeros function. So if I type this into my Python compiler, and I go in here and then I press run. Oop, I forgot to import NumPy. Import NumPy as np. And I run this. And let's print my array, and then let's print my array of 2. So when I do this, I get arrays of zeros, as you can see. And these two arrays are basically the same thing, except that one array is much more efficient than the other one. And if I print my 1, it'll show me an array of 1s, like that. But notice how there's a decimal point here at the end that represents that it is a float, okay? One other function is, remember we talked about the range function last time in Python and how we can use the range function, that we have our start value, our end value, and our step. We can have something very similar with np.arrange. And what arrange does, it's very similar. Oops. It has a start value, so the start value in this case would be 0, an end value, which is 20, and the incrementation value, or step, which is equal to 2. So if I print my array like this, what it'll do is it'll... I think I spelled that wrong. Arrange. There you go. It creates values from 0 to 4, 6, 8, all the way till 20. But remember, 20 is not included, so 20 is exclusive. Okay. I'm gonna have to change this on here. Anyways, linspace. What that basically does, so this is the one that I use the most often, and I can give a little backstory on this. Linspace creates an array that's evenly spaced. So the difference between linspace and arrange is that arrange basically creates, it's think of it as a range function, but linspace, let's say that I needed 100 different values. So if I know how many values I want to have in an array, and I know the start value and the end value, the NumPy will automatically create that array for me. So let's take a look at what this code is doing. It starts at 0 and it ends at 1, so these are our intervals, and I want to have 5 values within the array. And then I'm simply going to print the array. So if I run this, I have 0, 0.25, 0.5, 0.75, and 1. So I have 5 different values in my array, and that's what this 5 represents. And 0 to 1, that's just our interval of when we create our array. So I've used linspace many times to create time values for analyzing dynamical systems. So if I want to generate a bunch of times, then I would use linspace, as it's very convenient. So I could have time 0, time 0.25, time 0.5, so on and so forth. And our next function is the random function. And random function, they simply create random numbers, obviously. And if we use the standard random function, we would be doing np.random.random. And as you can see, this value here represents 3, so just 3 elements in that array. And if I print random, I get 3 random numbers between 0 and 1. So these could represent probabilities or distributions or whatever. but there's actually specific functions for distributions, which I won't get into. I will get into them when we talk about probability and statistics a bit more. And yeah, so we will be using random numbers to simulate situations, to estimate pi in random walks, which I did with my last class, but anyways. But if I want to set up a specific interval to declare random numbers, you'd be using random.randint. So what this function does, is it generates random numbers in between 0 and 10. So the first part is our range of random numbers, and then 3 here simply represents how many random numbers I want to create. So we talked about the different methods of NumPy arrays and how we can declare NumPy arrays. So I think there are 4: arrange, linspace, zeros, ones, and then random.randants and random numbers. I think it's not too bad, honestly, and I think that you should know all of them. So I will have you memorize them, and it's only 5 things. I think it's not too bad. Anyways, and I will talk about attributes of NumPy arrays. So remember from this diagram earlier above that we had a bunch of other information as well, and we're going to talk about what these information or what these attributes mean. And since you guys all know a bit of object-oriented programming, I can talk about it in that context as well. So similar to how we have 1D, 2D, and so on and so forth lists in Python, in NumPy we have these things called dimensions. So think of NumPy dimensions and shape this way. So shape simply represents what our array looks like on the inside. So how our array or how our NumPy array is actually structured. So it's usually within like this tuple looking notation. And the outermost list has 3 elements. So the first element simply represents how many lists does my outermost element have. So if I have 3, 4, 5 as my NumPy array, this would mean that the very outer list has 3 elements. And now the second number, 2 here, represents the second inner list. So here I have a list within a list, and I would have 1, 2 here, 2, 3, and 1, 0. So notice how each of the inner lists have 2 elements within them. Okay? And finally, the last number, as you can guess, it means that the inner list has 2 elements. So this is an example of a NumPy array with shape 3, 2, 2. And you can tell that the very outer list here, you see these outermost brackets, they have 3 elements within them, and each of the inner lists, they have 2 elements, okay? And that's how you get the shape. So whenever you use array declaration method within NumPy, like with random.random, random.random, or zeros, or any of the other functions, you can put in the shape instead of the number of elements. So whenever we put in the number of elements, this would give us a 1D array. But whenever we put in the shape, this would actually give us whatever shape that we wanted to use. So here, the outermost list would have 3 elements. The second inner one would have 3 elements, and then the final innermost element would have 2 elements. So you can kind of think of this as like a Russian doll. That's how I like to think about it. Russian doll. It's like those things that, not the Netflix show, but these little things where you keep on going in and in and in, and it's very similar to how lists behave, or how NumPy arrays behave. So just recall that you can either have the shape or the number of elements to create a NumPy array, and therefore you can customize your NumPy array very easily. And other than the shape, there are 4 key attributes of a NumPy array. So first is ndim, the number of dimensions. And what the number of dimensions represents is simply, I'll show you with this one. Oh, I should import this. Can I not copy from my PowerPoint? I cannot copy from the PowerPoint. I don't know why. Okay, I'll type it. x3 is equal to np.random.random. So I'm random.randoms. 10. Size is equal to 3, 4, 5. And all I'm going to be doing is printing the dimension. Print x3.dim, ndim. And if I run this function, I get 3, and that's because there are 3 elements. So I have 3 nested dolls, right? Or 3 nested, not dolls, elements, right? Or arrays. So, and then shape would simply return 3, 4, 5, because remember we explicitly declared the shape to be 3, 4, 5. And if I just print the array itself, you can verify that the shape is indeed 3, 4, 5. So the outermost list has 3 elements: first element, second element, the third element. And then the inner list, they have 4 elements each. And then the element on the very inside, they have 5 elements. Okay? The size, it simply refers to how many total elements there are. So if I print x3.size, it prints 60. And the way I get 60 is from 3 times 4 times 5, because that's just how combinatorics work, okay? And then if I do dtype, and we talked about dtype before, that just simply returns the data type of our array. So you have to kind of remember what all 4 of these do. So to summarize, ndim just finds out how many dimensions I have within the list. And in this case, you can remember it as how many commas I have here, or how many numbers I have within here. And then shape simply refers to how does my array look like. Size refers to how many total elements are there. And x3.dtype refers to the data type of our array. And finally, I'm going to talk about bits and bytes. So remember, a binary bit is the smallest unit of data, and I can turn on and off my bits and my bytes. And our computer can store these bits and bytes. And usually true is equal to 1 and false is equal to 0. I'm sure that you know this. This is kind of a bad way to use this, but if I do print true plus true, it'll print 2. Fun fact. Anyways, and this is something that you should memorize. 8 bits is simply equal to 1 byte, okay? And the memory of our NumPy arrays. So you can access how many bytes each element and how many bytes a NumPy array is taking up with this thing. So I don't know why, but I can't copy paste today. So if I print item size, I believe it was item size. Yep, item size. Then each element in here would have 8 elements, or would have 8 bytes. And then if I print x3 dot, and then the size of my array, or the size of the total array, n bytes, then notice how I have 8 here and then 480. So note how 480 is equal to 60 times 8, and remember 60 was the total number of elements that we had in our array. So just to summarize, n bytes is equal to item size times the size of our array, and this is kind of like an intuitive relation, okay? So that was just a basic, not a basic, but more of an in-depth explanation on how we can use numerical Python and the arrays, okay? And next class, we're going to be exploring some of the different methods that we have and how we can manipulate NumPy arrays and how we can work with them even further. But for this week, we just have to know how we can declare NumPy arrays, and that's it. Okay.